My name is Inder Kumar Rana. I am professor in the Department of Mathematics, IIT Bombay. I will be taking you through this course on measure and integration. This is a course which is normally taught at master's level, MSc in mathematics, and sometimes in departments other like physics, electrical engineering also. So, let us go through the basic objectives of this course. This course, as I said, is called measure and integration. This also goes by various names such as real analysis, advanced real analysis, and so on. The aim of this course, the objectives that we will be covering in this course are as follows. So, the aim is to generalize the concept of length, area, volume, etc., to abstract spaces, and that leads to the notion of Lebesgue measure on Euclidean spaces and general concept of measures on general spaces. And then also we will extend the notion of integration, which is normally done in UG levels called Riemann integration, to more general settings, and that leads to the notion of Lebesgue integral and other notions of abstract integration. So, these are the basic sort of outline of the course that we are going to follow. We will be following the textbook, An Introduction to Measure and Integration, written by me. This is published jointly by Graduate Text in Mathematics by American Mathematical Society, and an Indian edition of this is available through Narosa Publishers in New Delhi. So, why Lebesgue integration is needed and why what is the need for extending the notion of Riemann integration. There are some problems, drawbacks of Riemann integration, and to study about them you should look at chapter 1 of the textbook that I have mentioned. We will not have time to go through these drawbacks of Riemann integration and how efforts which were made to remove these drawbacks led to the development of Lebesgue measure, Lebesgue integration, and so on. So, for this we refer chapter 1 of the book. Historically, this was developed by the French mathematician Henri Lebesgue, who published as a part of his PhD thesis in 1902 integral longueur I, and then this was developed further into the abstract spaces by various mathematicians in 19th and 20th century, some of them being Emile Borel, Carathéodory, Radon, and Fréchet, among others. So, we will assume to start with, there are some prerequisites for this course which we shall assume, and we will hope that you have gone through an elementary course in first course in real analysis, and you are familiar with the properties of the real line. For example, what is real line, what are called open intervals, closed intervals, what is the topology on the real line, what are called the compact subsets of the real line. So, a basic course on real analysis is going to be assumed throughout this course. So, if you have difficulty in this, I would suggest look up some elementary book on first course on real analysis and go through these topics, so that you are not left behind and you are able to understand whatever things we are going to discuss, concepts we are going to discuss. There is one the basic space, of course, is the real line, but there is a notion of what is called extended real numbers, which we are going to use in our course. And since this is not normally discussed in most of the textbooks or in courses in real analysis, we will go through some of these concepts on extended real numbers. So, first of all, what is this set of extended real numbers? The set of extended real numbers denoted by R star is the set of real numbers to which we adjoin two new symbols. One is called plus infinity and the other is called minus infinity. Now, once we adjoin these two new symbols to the set R, we get the extended set are denoted by R star. Now, as you all know, the set of real numbers has got algebraic operations of addition, multiplication, there is an order on it. So, when we add these two new symbols to them, we would like to define how does these two new symbols, these two new objects behave with respect to the original order structure, the original operation of addition, multiplication and so on. So, we are going to define what are called operations of addition, multiplication and order on the set of extended real numbers. The first one is the order relation. So, we are going to assume or we are going to say that for every real number x in R lies between the two new symbols minus infinity, less than x, strictly less than plus infinity. So, this is how the new symbols plus infinity and minus infinity behave with respect to the order structure. So, minus infinity in R star is the smallest element and plus infinity is the largest element in R star as far as the order is concerned. For real numbers, the same original order stays. Next, let us look at the algebraic operations on R star. So, for real numbers x and y, we already know what is x plus y, but for infinity and minus infinity, the two new symbols, how are these operations defined? Here are the. So, for every x belonging to R, if you add minus infinity to x, you should get minus infinity. So, that is the rule we are specifying. How does minus infinity behave with respect to addition of real numbers? And similarly, plus infinity plus x is equal to plus infinity. Whatever be x, positive or negative, when added to minus infinity, you get minus infinity, and when added to plus infinity, you will get plus infinity. And now, how does infinity plus infinity added to itself? What is the outcome? So, it says plus infinity plus infinity is plus infinity, and minus infinity plus minus infinity is minus infinity. And let us specify that plus infinity plus minus infinity is not defined. So, these are the only four relations among addition of plus infinity, minus infinity with respect to x, plus infinity with itself and minus infinity with itself. Next comes the rules for multiplication. For every real number x, x into plus infinity is equal to plus infinity into x is plus infinity if x is non-negative, and similarly x multiplied by minus infinity is same as minus infinity multiplied by x is equal to minus infinity, again under the condition that x is bigger than 0. More or less we are following the rules of multiplication for real numbers. Similarly, if x is negative, so we have x multiplied by plus infinity or plus infinity multiplied by x is equal to minus infinity, the sign changes of infinity, and similarly x multiplied by minus infinity is equal to minus infinity multiplied by x is equal to plus infinity if x is less than 0. So, depending on whether x is bigger than 0 or x is less than 0, the rules for multiplication are as specified. Of course, if x and y are real numbers, the multiplication between x and y is same as that of real numbers. So, this is the rules for multiplication, and of course, there is a specific element, there is a particular element called 0 in the real numbers. How does that behave with respect to plus infinity and minus infinity? Here are the rules. For plus infinity into 0 is same as minus infinity into 0 is equal to 0. That is the same as for real numbers also, x multiplied by 0 whether positive or negative is always equal to 0. And of course, if I am multiplying plus infinity with itself, the answer is plus infinity, and if minus infinity is multiplied with plus infinity, the answer is minus infinity. So, plus minus infinity multiplied by plus infinity is plus minus infinity, and similarly plus minus infinity multiplied by minus infinity is minus plus infinity, the sign changes of the outcome. So, these are the rules for addition, multiplication and order structure on the set R star, which is nothing but the real numbers, along with two new symbols plus infinity and minus infinity. So, once again let us specify that the relations minus infinity plus infinity and plus infinity plus minus infinity are not defined. So, with these rules we get the set R star of extended real numbers, which is also denoted by this square bracket minus infinity comma square bracket plus infinity. So, that is essentially something like saying, like the real numbers are denoted by the open kind of interval minus infinity to plus infinity. If you close it on both sides, that is a notation used for extended real numbers. So, once you are familiar with the order, familiar with the addition and multiplication on the extended real numbers, we can look at the notion of sequences in real numbers, and also the notion of supremum and infimum on subsets of extended real numbers. So, let us first look at A is a subset of extended real numbers, and let us assume A is a non-empty set. Now, there is a possibility that A is a subset of real numbers only. Then we know that the completeness property of real number says, if the set A is bounded above, it must have least upper bound, or namely the supremum. Now, in the case A is a subset of R star, is a subset of extended real numbers, that means there is a possibility of minus infinity or plus infinity being a part of it. And suppose if it is bounded above, then it has to be a subset of real numbers and supremum will exist. If it is not bounded above, that means plus infinity is going to be a part of it. So, we will define the supremum of A to be equal to plus infinity if A as a part of R is not bounded above. And similarly, we will define the infimum of the set A to be equal to minus infinity if A intersection R is not bounded below. So, what we are saying is, in the subset of extended real numbers, a set which is bounded above or bounded below, we do not have to say that. So, every subset, non-empty subset of extended real numbers will always have supremum and will always have infimum. Of course, this supremum will be equal to plus infinity if the set A is not bounded above, and it will be equal to minus infinity, and the infimum will be equal to minus infinity if it is not bounded above. So, it is a very nice situation, every subset has supremum as well as infimum. Now, a similar conditions will hold, or similar results will hold for limits of sequences in R star. So, let us look at a sequence x n which is monotonically increasing and which is not bounded above. If you recall, as a subset, as a sequence in real numbers, if a sequence is monotonically increasing and is bounded above, then it must be convergent. And now, if a sequence is monotonically increasing and it is in R star, it is a sequence of extended real numbers and not bounded above, that means plus infinity is going to be an element of it. So, we will say if it is not bounded above, we will say a sequence is convergent to plus infinity and write this as equal to plus infinity. This is essentially also we say when x n is a sequence of real number which is monotonically increasing and not bounded above. In that case also we write the limit to be equal to plus infinity. So, for a sequence of real numbers, it is only a symbolic way of saying that a monotonically increasing sequence not bounded above converges to plus infinity, but as a sequence in R star, it converges to an element of R star, namely plus infinity. Similarly, a sequence x n in R star which is monotonically decreasing, and if it is not bounded below, we say it converges to minus infinity and write this as limit n going to infinity x n is equal to minus infinity. So, this is how we will analyze sequences in R star which are monotonically increasing or monotonically decreasing. Similar concepts can be developed for series in R. So, let us just say a few things about sequences, because every monotone sequence is convergent. So, if I look at the sequence, given any sequence, look at the supremums of that sequence from the stage j onwards. So, supremum k bigger than or equal to j of x k, then that gives me a new sequence, and that sequence will always converge. And similarly, the infimum from k bigger than or equal to j x k will also converge, because these are monotone sequences, and monotone sequences in R star always converge. So, limit of the supremum k bigger than or equal to j, for that is denoted by limit superior of x n, and similarly for the infimum k bigger than or equal to j x k is called the limit inferior of the sequence. So, in general we already know that limit inferior is always less than or equal to limit superior, and the sequence will converge when the limit inferior is equal to the limit superior, even in the case of sequences in R star. So, this is how sequences behave in. Now, let us look at sequence. From sequences, let us go to the concept of series. Suppose x k bigger than or equal to 1 is a sequence in R star. Then let us look at the partial sums of this sequence S n, that is the sum of the first n terms of the sequence. So, that is denoted by S n, which is summation k equal to 1 to n x k. So, for every n this is well defined, and one can ask whether this sequence is convergent or not in R star. So, if this series is convergent in R star, then we if the sequence is convergent in R star, the sum of partial sums, the sequence of partial sums, if it is convergent in R star, we say that the series is convergent, and the limit is called the sum of the series. So, this is basically same as that of real line, only keep in mind how sequences behave in the real line. So, with this basic discussion about what is the basic space of extended real numbers we are going to deal with. We start with a proper concepts in our subject, measure and integration. The first concept are going to be first few concepts are going to be discussions about class of subsets of a non-empty set. So, we are going to look at some collection of subsets of a given non-empty set X with certain properties. These collection of subsets, which we are going to call them as semi-algebras, algebras, sigma-algebras and monotone classes. These are various classes which play an important role later on in our subject. So, let us start with looking at what is called a semi-algebra of subsets of a set X. So, let X be a non-empty set, and let C be a collection of subsets of that set X. We say that the class C is a semi-algebra of subsets of X if it has the following properties. This collection C has the following properties. 1. The empty set and the whole space are members of this class X. So, the first property desired of C is that the empty set and the whole space X are members of this class. And the second one is that this class is closed under intersections. That means, if A and B are two elements of this collection, then the intersection of these sets A and B should also be a member of the class C. So, this class C is closed under intersections, that is the second property. There is a third property which we will describe soon, that is saying that this class need not be closed under complements, but will require additional property. So, let me write that property and explain, because it is best understood when it is written. So, X is a non-empty set, C is a collection of subsets of the set X. So, the first property we said empty set and the whole space belong to C, and second property was if A and B belong to C, then that implies A intersection B belong to C. And the third property, which is very crucial, is that if A belongs to C, then that implies the set, look at the set A complement, that need not be in C, but we want to say you can write C as union of elements C I, finite number of them, I equal to some 1 to n, such that C i's are elements of C and they are pairwise disjoint. C I intersection C j is empty. So, let us just go through these concepts again. A collection C in P x having the following properties. 1. The empty set, the whole space are elements of it. If A and B belong to it, then the intersection of these two sets, namely A intersection B, is also an element of this collection C. And the third property is, if A is a subset of C, then A complement, the complement of this set in X of course, should be representable as union of C i's, I equal to 1 to n, where these C i's are elements of C and they are pairwise disjoint. So, this property that C I intersection C j is non empty for I not equal to j, we just say they are pairwise disjoint. So, such a collection C is called a semi-algebra. Semi-algebra of subsets of X. So, let us look at some examples to get familiarized with this notion of semi-algebras. So, let us take let us look at some examples. So, let us take X any non-empty set. Let us take the collection C to be equal to all subsets of X. So, P of X, what is P of X? That is a power set of X. So, normally this is called the power set of X, which is same as all subsets of X. So, C is the collection of all subsets of X. Do you think it is closed under, so do you think phi and x belong to C? Obviously, it is a collection of all subsets. So, phi and x belong. Obviously, A intersection B also belongs to it if A and B belong to C, because if A and B are subsets of it, then naturally A intersection B also is a subset. And in fact, if A belongs to C, then that implies A complement also belongs to C, because A complement itself is a subset of X. So, A complement belongs to P x, it is a subset of X. So, belongs to P x, which is C. So, the collection of all subsets of the set X is a example, which is an obvious example of a semi-algebra of subsets of a set X. Let us look at some more examples. This was an obvious example. So, let us look at the second example, namely let us look at X equal to real line, and let us take the collection C all intervals in R. So, we are looking at the collection of all intervals in R, that is a collection C. So, first property, is empty set a member of C? Well, here you will have to understand, of course, yes, one way of looking at it is empty set can be written as the open interval a comma a for any point a belonging to R, and that is the interval. So, that belongs to the collection C. Second property, let us take two intervals I and j belong to C. So, does this imply the intersection I intersection j belong to C? So, that is the question. Means, if I and j are two intervals, can I say I intersection j is also an interval? Let us check in the picture. let us take two intervals I and j. So, let us say here is the interval I and here is the interval j. So, one possibility is that they are disjoint from each other. So, here I intersection j is empty. So, hence belongs to C. What is the other possibility? Other possibility is, let us take they intersect. Okay. So, here is my interval j and here is my interval I. Then what is the intersection of these two? So, this is I and that is j. So, that is my intersection of I and j, and clearly that is also. So, I intersection j is also an interval. So, it belongs. So, two cases, case 1 when they are disjoint, empty set, intersection is empty set and belongs to C, and if they overlap, then the overlap itself is again an interval and that belongs to C. Okay. So, it is quite clear that this collection of all intervals is closed under intersection also. Let us look at the third property, which is crucial, and that says if I take an interval I. So, the third property that we want to verify is if I is an interval, I should look at the complement of that interval and should be able to write it as union of C I equal to 1 to n, where C i's belong to C and C I intersection C j is empty for I not equal to j. So, once again let us look at an interval. So, let us look at an interval, say open interval A and B. So, that is my interval. Okay. So, what is going to be the complement of this? In fact, the complement of this looks like two pieces, one is this side, other is this side. So, this piece and this piece. So, for this I can write that the complement. So, R minus A B is equal to minus infinity to A enclosed union B to plus infinity, right. So, this is this part and this is this part. So, if I take an interval I, so that is I complement, where I is the interval A to B, then its complement is a disjoint union of two elements. Similar cases will follow if, for example, A is left open or right closed. So, let us write R if it is of the type this, then I can write this as if this point A is enclosed. So, minus infinity to A, the complement will be this open here and union B to plus infinity, and similarly the other cases. So, I will suggest that you write down yourself. So, we have verified C, the collection of all intervals in R is a semi-algebra of subsets of real line. Okay.